Interpreting a scatter plot can be somewhat subjective. So we also have a measurement that allows us to look at the strength and direction of our linear relationship. So if we look at a pattern and we can't tell if it's positive or negative because it's so weak, or if we are looking to see which is stronger between two graphs and it's hard to tell, which it was for a lot of your groups on that activity, the correlation coefficient is a good way to have a numeric measure of what that strength is. So it tells us these two pieces. Calculating that correlation coefficient is a gross ass formula. Hopefully parts of this formula do look familiar. So R is how we denote our correlation coefficient. We have our big summation symbol, and then we're supposed to sum this product of these xi minus x bar over s of x and yi minus y bar over s of y. So if you remember, x with a bar over it is a way to talk about the mean. S is our standard deviation. So every observation minus the mean divided by the standard deviation. This is essentially telling us to calculate this, we need to sum all of the z-scores for the x's multiplied with their corresponding z-scores for the y's and divide this by n minus 1. So calculating this by hand would suck because calculating a standard deviation by hand is not that fun. Calculating a mean by hand is not that fun. We need to have z-scores for every single observation for both the x and the y variable and then do this summing. But as you saw on that activity, if you have that diagnostics on in your calculator, you just enter the two lists and it pops out the answer for this. So in order for us to actually get a correlation coefficient, we need to have quantitative variables. There are measures for categorical variables, but they're not this standard correlation coefficient. They're special measures. We need to see a linear trend. This only describes the linear relationship. So if we have something nonlinear, our measure is not necessarily going to be accurate. It's very sensitive to outliers. And then our last piece here, we should have things that do have that nice, if you looked at the histograms for both your x and your y, nice bell curve shape. They should both be symmetric without outliers. Once we get our correlation coefficient, it is going to be bounded between -1 and 1. At the very most, it's 1 or -1. If it is 1 or -1, that means every single thing fell on a straight line with a positive slope. So here are two examples of something that would have a R of +1, exactly. So we could have something like this. Imagine those are actually on the same line, and then I can draw. This is getting terrible. I'll start over. So whatever your line, you get 1, then there's another one, and then maybe 1, 2. So you can see every single point falls straight on a line. There's no variation away from the line. Everything is directly on it. They don't need to be equally spaced out or anything, but that would have an R of 1. Another thing that would have an R of 1, doesn't matter what the slope is, it just needs to be positive. It could be a much smaller slope. Something like this. Imagine those are in a straight line. Both of those could have an R of 1. An R of -1 would be the same thing, just with a negative slope. If it's close to 0, that means our relationship is very weak. But there's a lot of variability away from the trend. An R of 0 means that the data would have a slope of 0. That best fit line would have a slope of 0. So just because you have an R of 0 does not mean there's no relationship. In fact, it's one of my favorite questions put on the first exam. It's just a true-false question. So here's my example. Something that has a R of 0, correlation coefficient of 0, but usually what this means is that our data is just, there's nothing going on, right? 0 trend. So when it tries to fit the best line, the best thing is just to go to the mean. But that is not the only case. Another example having an R of 0 would be something that has a quadratic relationship. If you try to fit a line to this, the best is going to still be a straight line, right, with a slope of 0. But there's definitely a trend here. There's a strong relationship. It's just nonlinear. So don't assume because our R is 0 that there's nothing. In fact, that's a big mistake that researchers will make, is they won't look at a scatter plot. They'll just look at the correlation, see it's 0, and assume there's no relationship and not even bother to investigate. And then our last piece here, since it uses z-scores, there's no more units anymore. So if we're thinking about that cricket chirp example, if I changed from Fahrenheit to Celsius, it's still going to have the exact same R. You can even think of the scatter plot. It's not going to change. We're just going to change the scaling on that x-axis. So we do have some guidelines here on what is a strong versus a weak relationship based on our correlation coefficients. Basically, close to 0.5 is moderate, and then the closer we get towards 1 or -1, we're getting a stronger relationship. The closer we are towards 0, a weaker relationship. And then you get the most important thing here. This is the interpretation, something I might devote a little note card space to. This particular section of the lecture notes, we have a lot of sort of canned responses of how we usually think of particular parts of this linear regression correlation stuff. So if we have a correlation coefficient and someone says, go ahead and tell me what this tells us about the relationship, you need to tell me the strength, the direction, you need to have the word linear, and then throw in what your variables are. Give me some context. So we're going to do this on the next page, and you can see what this looks like in action, and I'll talk about what the point totals are for the test as well. So here we have some examples of scatter plots. These did not line up very well, and their corresponding correlation coefficients. Ugh, this has never happened before. It's the first. You can see 1 and -1, perfect straight line. As we move further, 0.7, we're already seeing a lot of variation away from that trend, right? 0.8, still a lot of variation. And then by the time we're at 0.3, it's almost impossible to tell there is a trend there at all. The easiest way to see that there's a trend is to sort of see these big open spaces and go, well, I guess they're going through that corridor with a positive relationship. And then 0 just looks like a mess. So we're going to go ahead and kind of guess what our correlation coefficient would be for this particular data set. This is not something I have you necessarily do on a test. I might have you match graphs to potential correlation coefficients, but I'm never going to say, here's a graph, what do you think the correlation coefficient is? But we can do this. First thing, should it be a positive or negative correlation? Obviously here our R needs to be negative because our trend is negative. And then we can kind of look back up at those drawings and say, well, which is this the closest to? And I'd say that this is somewhere between the 0.07 and the 0.8. So let's just call this a 0.75. So that's our correlation coefficient. Now, the second part of this, the interpretation, is the piece that you guys will need to be able to do on an exam. So I'll go ahead and do this with you for this one. I hopefully have an example later. We don't. So we're going to just fill in the blanks from that previous page. There is and then we need to figure out what the strength is. So 0.75, well, if we looked back at our little cutoffs, 0.75 puts us at the moderate level, right? But it's also right about strong. So if you're in something like this, especially here where we guessed what our thing was, and on a test, I don't think you need to know those little cutoffs. What you can do is you sort of hedge your bets. So there is a moderate to strong. So in this case, I'm like, okay, it's somewhere right between the two. So let's just say it's in between. There is a moderate to strong. Then we need our direction. And we have a negative linear relationship between, and we need our x and y variable, latitude. We don't need to put in the units because remember, this has nothing to do with units at all. It is unitless between latitude and temperature. It does not matter the order you do your x and y either, because essentially the formula, if you remember, doesn't matter which is x and which is y because we're just multiplying them together. So we can get rid of that. Now, in terms of points, on a test, I almost always have you do this. It's almost always a free response question, and it's worth 3 or 4 points. There's always a point for having moderate to strong, the strength, and having it correct. A point for remembering to tell me the direction of the relationship. A point for having the word linear in there. Just remember, this is sort of a limitation of the correlation coefficient. It can only talk about the linear relationship that exists. And then making sure you give me some context is worth a point. So these are the 4 pieces that I need to see on the test for you to get all your points when it comes to interpreting your correlation coefficient. So we do have some possible problems. Correlation does not mean causation, especially if we don't have an experiment, if we're just looking at an observational study. It only gives us information about the linear relationship, like I said. And just because we have a strong correlation, there could be something else going on. We could have what we call a lurking variable, which we didn't really define in the first step. I actually took that out. But a lurking variable is something like, a strong example is that there's a high correlation between shark attacks and ice cream sales. Strong positive correlation that shows that as ice cream sales go up, so do shark attacks, or vice versa. So the question is this a real relationship? Is there some causal piece, right, between shark attacks and ice cream sales? Either direction. And hopefully we immediately go, no, there's a confound or a lurking variable here, the time of the year, right? During the summer, there's more people eating ice cream, cooling off, and also more people on the beach potentially getting attacked by sharks. So we got one last example here sorry, I'm glancing ahead because I'm like, how much do I need to do? One more example here and we're done with correlation. We're going to just go ahead and put these things in our calculator, see what we get. Frankly, you can skip this. You do not need to do this part because it's very much what we did in the activity on Thursday. So feel free to skip this part, but if you want to see more, I'll work through it with you. In this example, we're looking at number of deaths and magnitude of 6 earthquakes. We're going to go ahead and first, we're actually going to be bad. We should look at the scatter plot first, but we're going to go ahead and calculate that correlation coefficient before we look at our scatter plot and make sure we have a linear relationship. To do this, remember, you're going to enter all your x variables in L1 in your calculator and all your y variables in L2. You need to make sure you have diagnostics on, which I described in the previous page that you can go through, or I walked you through it in the activity, so it should already be set up that way. And then pop out your linear regression output. According to my linear regression output, our R here is 0.7317. So if we were to interpret that, and this is the one thing that would be worth doing, is take a second, pause this video, and interpret your correlation coefficient. So if you did that, you should have written down there is a moderate, or moderate to strong is fine, positive linear relationship between, oh, that's a lot of E's, between magnitude of an earthquake and deaths. Okay, so let's look at our scatter plot. If we created a scatter plot for this, this is what your scatter plot would look like roughly. And if we look at our description based on that correlation coefficient, that's not really describing our scatter plot, right? So based on our graph, do you think that's accurate? No, not at all. What do we see in the graph? We see what looks like maybe a negative trend with one fat outlier, right? So I'm not going to bother to write that down, but that's what we see. We do not see a moderate positive relationship. We see a negative relationship with one very large outlier. So what we can do is we could go into our calculator and we could remove that one outlier. So in your list, you just want to get rid of this particular value and we'll recalculate. If you were to do that, and I have to listen to me click around my calculator because I'm too lazy to pause. Whenever I pause a video, it makes me like, counts me down to get back in. It's super annoying. It's a waste of time. All right, so now my R is equal to negative 0.9595. Now our interpretation of this would be there is a strong negative linear relationship as opposed to a strong positive linear relationship. So this is one of those examples where we can't just keep the outlier in, we can't take it out. Our outcomes are very different, so we would need to come up with some sort of way to talk about this or some sort of method that would get rid of that or collect some more data to really look at this, because a strong negative trend doesn't really make sense. It doesn't make sense that as the magnitude of the earthquake goes up, the number of deaths goes down. And there's probably a lot of confounding variables. So this particular data set is a little bit silly. Boom.